So recall, in the first part of the lecture, we've seen how this communication setup led to these very fine-grained lower bounds for hardness approximation. So we've seen the entire proof, except for the proof of that amazing communication protocol, right? So very, very quick reminder was, right, we had this communication setup where Alice and Bob each receive a string. They get a shared input, like shared randomness, and they receive this non-deterministic advice. But the non-deterministic advice does not see the randomness. Now we'll see the proof of this theorem that, in fact, you can give this highly non-trivial protocol with an improvement from like the naive message length of BD to root D. But before we do that, we have to talk about polynomials, or let's say basic facts of polynomials. So maybe just very quick show of hands who of you are familiar with, like, let's say polynomial interpolation, something like that. Okay, good. I'm nevertheless going to give you some, easy facts. So that we're on the same page. Actually, good. Think of some field F. If that scares you, just think of, the reals. The first and very simple fact is, every degree T polynomial over that field, in fact over an arbitrary field, has at most T roots, right? Which is points on which that polynomial, we call P, becomes 0. Okay, that is either extremely trivial if you've seen it before, otherwise it's also not that hard to see. If this is some polynomial, then these are the roots. And you can have at most T of them if the polynomial has degree T. Sure. Here's a second fact. By the way, I should mention, this part of the talk is much shorter than the other one. Like the proof of the protocol is really short, but magical. So you have to appreciate it. Fact 2. This is called polynomial interpolation. Okay. It says this. If you're given distinct elements x1 through xt, and arbitrary, meaning not necessarily distinct, elements y1 through yt, all of which are from our field, there is a degree T polynomial P such that it has exactly these evaluations. So P of xi is equal to yi for all I. Okay. Pictorially, this means that if you fix some points, I don't know, like these, this would be x1, y1, maybe this would be xt, yt. There is a polynomial which you can fit to these points. Whatever, something like this. And this polynomial has at most degree T. The proof is so simple that I'll write it down. The proof is this. Let's verify. I claim this polynomial evaluated at some point xi equals yi. So plug in xi into this polynomial. Then this is either equal to 1 if x is equal to xi. Because xi minus xj divided by xi minus xj is 1. Or this part is 0 if x is equal to some xj, which is not equal to I. Okay? Which means that if you plug in xi, then in this entire sum, all the terms are going to vanish, except for the ith one. In the ith one, this entire product here, in the ith one, I want to include this in the bracket here. Sorry. Okay, all terms in the sum are going to vanish because, let me start over. Maybe this was a little bit confusing. You plug in xi. The claim is all these products, all these terms in the sum are going to vanish except for the ith one. In any other term j, right, you would find that the j in the product, which would become 0, which makes it vanish. Only in the ith term, this will evaluate, like all these entries in the product will be evaluated to 1. Okay? Which means that only the term yi remains. All the other ones are killed. So the product really is, the output really is yi. Okay? Good. Polynomial interpolation. Works over any field.
What about the degree?
What about the degree? Yeah, good point. So these are all constants, right? So really this is the only one which matters. And we take a product of at most t minus 1 of them. So I guess it's even a t minus 1. Yeah. Is that right? Yeah. T minus 1. Good. OK. That's it. That's all the facts we need. Let's talk about the protocol. And I cannot offer you that much intuition about it. Maybe like use a tiny piece of intuition. So we want a protocol in which Merlin takes up a significant share of the work. Merlin really is our powerful resource which we'd like to exploit. And we have like basically two extremes. Either Merlin just tells us the answer right away, which is great because it has a lot of information. Unfortunately, we cannot do that because we cannot trust Merlin, right? So the one extreme, Merlin sends us 1 bit, perfectly trusted, but unfortunately it doesn't work because we're not trusting it. On the other hand, if you don't trust Merlin at all, right, then we get back to the situation where you basically ignore Merlin, so you only have randomization, so you send basically d bits. Let's say Bob just sends its input to Alice. So in the other extreme, we have like the communication is just d bits. We do not rely on Merlin at all. So what we should do is we should somehow find a point in the middle. We should let Merlin send something, which is on the one hand informative enough that we can extract our answer from it, but on the other hand is easy enough to verify whether Merlin is cheating. Okay? And it turns out that the right answer as to what Merlin should send is a polynomial. And what exactly that polynomial is, we'll see now. So here's the protocol. We have to fix a field. Let me quickly do it, but don't worry too much about it. So we actually choose a finite field because we want to send around field elements. So we cannot choose something like the real numbers because they would need like an infinite number of bits to send around. So we'll actually choose a finite field of an appropriate size. Let's say for some prime in like 200D to 400D. These sizes don't matter much. The only key is there is a prime of size at least 200D, which is not too large. Let's take one of them. Now, let me assume that d is a square number, so that I can write t to denote root d. Consider the following polynomials. By interpolation, there exists degree t polynomials guess it's t minus 1, who cares, that satisfy the following. Pi evaluated at some point k is x of I times t plus k. And qi evaluated at k is y at the same point. It's a little bit abstract. I'm going to write a picture. Okay, so what do? We take a vector x. By the way, yeah, for x and y are like the inputs of of Alice and Bob, right? So take Alice's input, view it as like a bit string, and we chop it into t parts of size t. Then the first part will be modeled by the polynomial p1, the second one by p2, and so on. And if the first part had like a 0, 1, 0, 0, 1, I don't know, then we interpolate the polynomial which had like a 0 here, a 1 here, a 0, 0, 1, you know. I don't know, something like that. This will be our polynomial p1. Same for all the other ones. In the end, you have pt. Okay? And we do the same for y. Good. The magic is this. Magic is finding this polynomial, which I'm about to write down now. Okay, so we take a polynomial phi of x, which is defined as the sum over all polynomials, pi times qi. We'll basically take like an inner product of these again, which is exactly what we should do. My question to you is, first of all, what's the degree of this polynomial? Sorry? D? D. Actually, it's smaller. 2t, exactly. Because each pi has degree at most t. Same for each qi. We take a product of these, which means degree 2t for all of them, but this is a sum. Sums do not increase the degree. It has degree 2t. And the more important observation is this. What is this sum? I sum up over all elements 1 to t, the values of that polynomial at these points. Good. AKA? AKA, how would you call that?
I mean, just the inner product.
The inner product. Exactly. Let's verify, just very quickly. I mean, okay, by definition, this is the product of. Sorry, we sum over all k's and all i's, the product of pi of k times qi of k. But by like the way we interpolated these polynomials, this is really just a complicated way of writing down the inner product. Sure. Right, so on the left-hand side, I've expanded the definition. I've said, OK, the phi is just the inner product of a bunch of pi and qi polynomials. And then if you sum both over the index I of the polynomials as well of the evaluation point k, turns out you really express the inner product that way. Because every index of the inner product can be written in the form I times t plus k. I guess I'm making some plus minus 1 errors in here because actually you should start from 0, but ignoring these, that's correct. OK? Good. So this is the key idea behind the protocol. Can you see? Actually, I need that fact. Let me continue over there. And I need my. OK, no, I'm not going to ask it. I'm just going to tell the protocol right now. The protocol is this. The randomness is view R as a random element of our field. The Merlin, or what's Merlin supposed to do is rather this. He is intended to send the polynomial phi. The entire polynomial. There's several ways in which he could send it. Let's say he sends the coefficients of phi. What does Bob do? Bob sends the following. He sends, the polynomial q1 evaluated at R, q2 evaluated at R, up to qt evaluated at R. And then Alice does the following. First, she evaluates phi of R. Namely, indeed, recall that this is just the sum of all i's. Pi of R times qi of R. And she indeed has access to that. On the right-hand side, note that she has access to the qi of R, qi's of R, because that's what Bob sent her. And the pi's of R are these polynomials which are only defined with respect to x. OK? Same argument, by the way, is necessary to say that Bob can even send the qi's, because obviously they depend on y, and Bob knows y. OK? Good. And then she accepts exactly if the following conditions are satisfied. Well, I guess. She accepts if condition 1, whatever Merlin is sending is the same as what you would expect. Oops. No, it's great. So Merlin is indeed intended to send whatever his message is intended to be it's like the polynomial phi, but Alice makes sure of that by saying, well, maybe at this particular evaluation point, I can check. And the other thing is she has to make sure that the vectors are actually orthogonal. And for this, she's now going to trust Merlin. And Merlin says, well, I send you the polynomial phi, and from phi, you can read off the inner product. So the second thing she's going to check is if the sum of all elements k, evaluating Merlin at k, is 0. Let me put it up there and talk a little bit about the protocol. Remember the two issues from before, right? We wanted Merlin to send something which is on the one hand expressive enough such that you can verify, such that you can extract some output out of it. You can learn whether the vectors are orthogonal. This is intended, like if Merlin actually sends the polynomial, the magic polynomial from over there, we can do it. Because from that polynomial, by the observation over there, you can extract the inner product. So really the second check is to say that we trust Merlin and he's going to give us an actual answer to the communication question. But at the same time, we have to make sure that Merlin is not cheating. So we have to be able to verify whether Merlin is talking nonsense. And for that, we say, well, maybe we cannot completely verify whether the polynomial phi matches whatever Alice and Bob want to communicate. But we can randomly verify. We just evaluate at a random point and test whether at that particular point Merlin was cheating. It's also called polynomial identity testing, what we're doing here. OK. We're basically through. The analysis is very short. Maybe I'll erase this. I guess we have the setup in mind by now. Yeah. Well, we have to prove three things. On the one hand, we have to prove completeness and soundness, and we have to give an upper bound to the parameters. Let's start with completeness. Completeness says if the inner product is actually 0, then there is some good advice by Merlin which makes us accept. So what should Merlin send? Yeah. I guess I asked this a question, but I already written it. Merlin sends the polynomial phi. Which, OK, clearly implies that the first check is not going to fail. Because Merlin really, whatever he sent, these polynomials are equal on every point. In particular, they equal on the random point. First check will not fail. But on the other hand, we have that by the observation over there, that if you sum up all the points in Merlin's polynomial, that's the same as summing all the points in phi, which is just equal to the inner product, which, if it's 0 in the completeness case, means that also bullet 2, test 2 accepts. Good. Let's talk about soundness. There's two cases. Merlin could try to cheat or not cheat. Let's have the first one first. Let's suppose, I don't know why, but suppose Merlin would truthfully send the right output. Merlin sends m equal to phi. Well, then by the same calculation, actually the sum of the m's, like the sum of the evaluations of our polynomial m, is just equal to the inner product, which means that we're going to make bullet 2 fail, or test 2 fail. In the case where, for For the soundness case, there we can assume the inner product is not 0. We have to figure that out. So if the inner product is not 0, then in particular, our second test is going to fail. Good. Now let's get to the more interesting case, which is Merlin tries to cheat. Merlin sends some polynomial m, which is not the same as phi. Like, as a technical remark, we can always assume that he sends a polynomial, and even a low-degree polynomial, because if Merlin wouldn't, we clearly have caught him in a lie. So we can always assume that Merlin really sends a polynomial. Well, but in this case, let me write it down. Merlin sends some degree at most 2t polynomial. Same argument as before. If he sends a polynomial with higher degree, we anyways reject, because phi would have degree 2t, right? So then the probability that we accept, or in fact that the test 1 accepts, which was this, right? That actually the polynomial, whatever Merlin sends, coincides with our actual polynomial in the random point. This is literally just the probability that these two polynomials coincide. And let me write it slightly differently. This just means that the difference polynomial has a root at this point. Difference polynomial m minus phi. But fact 1 tells us that every polynomial of degree 2t, and this is a 2t degree polynomial after all, right? Easy to verify, has at most 2t roots. So in particular, the probability that this happens is at most 2t over the number of all possible values which we could pick, which is p. Okay, and now the parameters just work out. T is, even where the very crude upper bound is at most, let's say, d. So then this is 2d. P we've chosen to be larger than 200d. So it works out. It's even square root d, but that's bounded very naively. OK. Are you convinced about completeness and soundness? Good. Final step is the parameters. Nice, I'm going to reuse this. Well, it's just one line, basically. Or 3 lines. How many bits of randomness do we send? Sorry? There was an answer? Maybe not? Log? Log p. Log p. Nice. Log p, well, because you have to send one field element. The field is size p, so if you just arbitrarily name the field elements by some bit string, you need log p strings. Ceal for odd numbers. How many non-deterministic bits do we send? What was that? 2t log p. Yes. So again, we have to communicate field elements. This time it's not a single one, though. We have to communicate a degree 2t polynomial. And a degree 2t polynomial can be represented in particular by, say, 2t coefficients, each of which requires that many bits. So this times 2t. Finally, how many bits does Bob send? Anyone? Nice. Good. So again, some field elements, but Bob really sends t of them. Well, because the protocol tells us that Bob sends the evaluation of his polynomial at array. Good. And now, well, this is just log d. T we chose to be root d, right? So this is log d, this is root d log d, and this is root d log d. Okay, so you can see there's even some slack in what the theorem is claiming, right? Actually, the amount of randomness is much smaller than root d, just logarithmic. Also, I've said this before, like, if you think about these parameters very carefully, the gap actually had a ridiculously small dependence in there. The gap was really just, we wanted to argue that polynomial identity testing succeeds with some probability. So we wanted to have that P is sufficiently large. But P only has a logarithmic dependence in there. So you can actually make the gap much larger and still get away with it. But for simplicity and for like our purposes, this is already sufficient. Good. Any questions? Okay. So yeah, I think I didn't want to say it before, but this was really like the most technically involved part of the entire lecture, I'd say, like at least these 2 lectures. So you successfully made it through that. We'll have one more afternoon session today, where I'm going to talk about something which is actually kind of related to what's going on here, at least non-determinism is going to show up. And then tomorrow you can relax when Amir is going to give you like an outlook beyond whatever we've discussed. One remark, you've seen the exercise sheet. And today it's really time for you to apply what you've learned over the last couple of days. So this is really like simulating the research you would do, right? You're given a problem, you're working on this. Actually, I've talked to a couple of you, and some of you even have a problem in mind to think about, right? So now we give you some problems, and you just have to work on it without us telling you what you have to do. So hopefully that's fun. See you in the afternoon.